Now in this lab activity you will further analyze the noise reduction properties of ensemble averaging. In the first lab activity we have seen how ensemble averaging reduce noise. Now you will see or will prove that ensemble averaging actually reduce the noise by under root n times, where n is the number of responses which we will take to get ensemble average. In this lab activity we will use actual whir. So the first step in this lab activity is to load your signal and check the orientation and size of your data. If size and orientation of your data is according to the requirement, or there is no need to take the transpose of matrix, so after completing this step, the second step will be estimation of ensemble average. First we will estimate the ensemble average of 100 responses, then 25 responses, and then we will estimate noise component in each ensemble average. After estimation of noise component of each waveform, we will compute standard deviation. Standard deviation of each noise component, and will compare how ensemble averaging reduce noise. So let's start with the first step, that is to load the signal. Sampling frequency A will be equal to 1 divided by 0.005 because the sampling interval of these responses is 5 milliseconds. Then you have to check the size of your data. For this you will call size routine of the MATLAB, and the input to this size routine will be whir. If rows is greater than columns, then there is need to take the transpose, and then you will generate time vector. To plot the signal with respect to time. If data is according to the requirement and the orientation of data is such that the responses are stored row wise, so there will be no need to take the transpose. In this case you will need to just define the time vector. Now and the if structure. Now the second step is to compute ensemble average of 25 responses, 100 responses, and plot each responses and also plot the individual evoked response. So average 100 will be equal to mean whir. So this is the ensemble average hundred responses, average 25 will be equal to mean. Now you need to access first 25 responses, so the input to this mean will be first 25 rows of the matrix whir. Therefore 1 to 25 comma colon this is the ensemble average of 25 responses. We are also required to plot these responses. Therefore, we will use subplot command. There will be three graphs. First graph will show individual evoked response, the second graph will show ensemble average of 100 response, and third graph will show ensemble average of 25 response. Therefore 3 comma first we will plot individual evoked response, that is the first response of the matrix were. So this is the first response of the matrix were. X label of the graph will be time, Y label will be EEG signal, since this is the visual evoked response and visual evoked response is an EEG signal. Now in the second window of subplot, we will plot ensemble average of 100 responses with respect to time. X label will be time, Y label will be EEG signal. In the third window of subplot, we will plot ensemble average of 25 responses. So 3 comma 1 comma 3, plot T comma average 25, X label will be time and Y label will be EEG signal. Now this completes the second step. The third step is to estimate noise component. To estimate noise component, we need to subtract this actual work. Actual work is noise free work from the average 25 and average 100 responses and from the individual evoked response. So whir noise will be equal to one comma colon minus actual whir. So this expression will estimate the noise component in individual evoked response, that is first evoked response. Similarly, we will repeat this formula for ensemble average of 100 responses and 25 responses and estimate noise component in these ensemble averages. Similarly, for 25 responses, average 25 noise will be equal to average 25 minus actual work. Sample average of 25 responses. Now the third step is to find the standard deviation of these variables: var noise, average 100 underscore noise, average 25 underscore noise. That is to estimate the standard deviation of each noise component. So we will use STD, standard deviation routine of the MATLAB, where STD will store standard deviation. Here I have initialized a variable word underscore std. This will be equal to std so this expression will estimate standard deviation of the noise component of individual evoked response, that is first response stored in matrix var. Similarly, for 100 responses and 25 responses, std 100 underscore 100 This equation will calculate standard deviation of the noise component in the ensemble average of 100 responses. Similarly, for 25 responses, noise. We will need to display all these variables in the command window. Therefore, we are using this command. Now run this code to get the output. From the command window, there is the standard deviation of one response is 1.0405 and standard deviation of the noise component of ensemble average of 100 response is 0.1005, and for 25 responses it is 0.1986. From this result you can see how ensemble average reduce noise component. It actually reduced noise component by under root n time, where n is the number of responses. So when you divide 1.0405 by 10, you will actually get the result which will be close to 0.1005. Or for 25 responses, when you divide 1.0405 by 5, you will get the result which will be close to 0.1986. Here the practical values is not accordingly to the theoretical values, but they are very close to the theoretical values because noise is a random process. Now you are supposed to repeat these codes and attach plots with proper inference in your lab manual. You are also supposed to complete post lab tasks given in your lab manual. Thank you.